So looking at the applications of first law, one of the important ones we had seen was the general polytropic process. Wherein if pressure and volume are related by an equation like this, or we can say pressure is proportional to V to the power minus alpha, where alpha is any real number, then the molar specific heat capacity becomes F by 2R plus R upon 1 minus alpha, and Q becomes NC delta T from this, and the work done by the gas becomes NR delta T upon 1 minus alpha. Okay. So this was a very important application and general formula, because we can see that even the 4 standard processes can be thought of like special cases of polytropic process. So isothermal, that is the case where alpha is equal to 1. Isobaric, that is the case where alpha is equal to 0. Isoporic, that is the case where alpha tends to infinity. And adiabatic, that is the one where alpha is equal to gamma or Cp by Cp. Also for isothermal, we saw that C is undefined. For isobaric, we saw that C is equal to Cp. For isoporic, we saw C is equal to Cb. So this is a very easy way to remember all these specific cases. So this C is equal to 0. So let's look at an example today. So we have, for a given process, temperature is proportional to 1 upon V square. And a sample of helium is expanded from an initial state like this to a volume of 2 liters. So we want to find the pressure and temperature in the final state, and we want to find out Q, W for this. So you'll see that you can approach this like an indirect application of polytropic process. Just try out this question.
Sir, do we have to write the upper part, that recap one?
Not necessary. You have written all this down in the previous lecture. It's a quick recap. Mainly see how you'll apply this information for this question.
Okay, sir.
So last time we had seen the derivation of these formulae also, no? That
yes,
for
sir.
polytropic process, how we get this particular set of formulae.
So we have doubts in HC1 question.
You have doubts in which part, beta?
HCV question.
Yeah, but from these chapters, first law and CPCB chapter.
Sir, we are remaining with all the doubts of all the chapters.
Define all.
Means this heat and thermodynamics,
Heat
mean
and
heat
thermodynamics.
and
Means you have some doubts
temperature.
from calorimetry also.
Yes.
Yes,
Okay.
sir.
Yes, sir.
Thermal
We'll discuss.
temperature.
Okay. Thermal temperature you should not. Okay, we'll discuss. That's a very easy chapter. Anyway, we'll discuss. Okay. So let's finish cyclic processes in few minutes and then we'll keep time aside for doubts.
Sir, should we do that in a single lecture at last?
Sorry?
Should we do all that in last lecture of after chapter finish?
No, no. After this, there is heat transfer also. So don't worry. Okay. We'll clear the doubts of thermodynamics first. Then only we'll move on to heat and
Okay, sir.
to heat transfer. Okay. Because that is an unrelated section, but all these things are related to each other. The kinetic theory of gases, first law applications. So can you tell me the relation between pressure and volume for this process? The relation given is between temperature and volume. So convert it to a PV relationship and see what kind of quantity you're getting. So that will tell you how to apply the equation of polytropic process then. Yes, so that's correct. Kanishk and Yash Bhaviskar. So temperature is proportional to 1 by V square. That means pressure into volume is proportional to 1 by V square, or PV cube is constant. That is a pressure volume relation, because so that is the first thing we'll understand. So it's a polytropic process. With C equal to CV plus R upon 1 minus 3. So CV minus R by 2. And W equal to NR delta T upon minus 2. So this is that interesting type of process where if the temperature increases, there's actually a compression happening. Work is done on the gas. So anyhow, so now let's look at this. So T2 by T1 will be equal to V1 by V2 to the power 2. So that's how V2 should become V1 by 4. Oh, sorry, I've got this reverse. Temperature should become because I've doubled the volume. So the final temperature should be 50 kelvins. And therefore the final pressure, you see, temperature has become 1/4 and volume has become double. So pressure has become 8 times. Okay. So typically any ideal gas under such extreme conditions of very high pressure and low temperature will actually not behave according to the kinetic model anymore. But in this question, we'll just have to assume that even under extreme circumstances like this, the gas is more or less behaving like an ideal gas. So if we actually do this kind of an experiment, the results are not going to agree very well with the theoretical results that we are getting by this method here, because it's a very high pressure and very low temperature. So the properties of the gas will start to change with respect to ideal gas. Yes, exactly. No? So pressure is
Excuse me, so how did you get the value of P2 as 8 ATMP? Can you please explain
okay.
it?
So T2 V2 upon T2 should be equal to T1 V1 upon T1. So P2 should be T2 by T1 into
Sir, it will be 1/8.
Oh, sorry, yeah, that. So very low pressure. Okay, so 1/8 of an atmosphere. So that is
1/8.
0.125
Yeah.
atmospheres. Okay, so extremely low pressure, but that should not be so much of a problem actually compared to high pressure. So, or you can use this also, that pressure is inversely proportional to V to the power 3. So P2 by
Sir, I did
P1,
the same.
yeah, cube. So you
Can
can see it should become now V2 is 1/8. I mean V2 is 2 times V1. So you can see that V2 will become this also. Okay, so that is this thing done. So we have got the final pressure and temperature. Now Q and W, let's find out. Okay, so the molar specific heat capacity, as we saw earlier, is Cv plus R upon 1 minus 3 in this case. So helium, it's a monoatomic gas, so it's very simple, 3 by 2 R minus R by 2. So molar specific heat capacity is R. So Q is equal to nR delta T. So that is P2 V2 minus P1 V1. So we are actually withdrawing heat from the gas, I think. Okay.
Minus 75.
So 1 by 8 into 2 liters minus 1 into 1. This is into 101 typically to convert to joules. And take it approximately 100 also. Okay, so it's a negative quantity minus approximately minus 75 joules is Q. And W is nR delta T upon 1 minus 3. So it will become plus 37.5 approximately joules. So if you visualize the PV graph of this particular process, it's a very extreme kind of situation. So if you compare this process with an, for example, an isotherm, isotherms will be like this in comparison. It's falling much more rapidly. So the temperature is decreasing as the volume is increasing. So Q is negative, W is positive in this particular process as you're going from 1 to 2. So anyhow, so you can get these type of questions. Okay, you can, for example, also get indirect questions where some graph of temperature, volume, or pressure and temperature, etc., will be given. So you want to note down. So finish this. Okay. So you can always convert the information from the graph or the given equation of either pressure temperature or volume temperature into the relation for pressure volume.
Sir, can you please explain the graph once? Sir, your voice is very low, sir.
Sir, your voice isn't coming.
Yeah, sir, it is coming, but it's very much low. I think you are away from the mic. It's coming as if you are very much away from the mic. Sir, even now it's coming like that. It's coming as if you are away from the mic.
Okay, so are you getting the audio properly now?
Yes, sir.
Yeah,
Yes,
that
sir.
would be
Yes, sir.
great because- Yeah, so coming back to this, somebody asked about the graph. So the graph is of this type. Now, pressure is inversely proportional to 1 by V cube. So it's a y is equal to 1 by x cube type of graph, or y is equal to some constant by x cube. So it's hyperbolic like this. Understanding?
Yes, sir.
The graph is clear now?
Sir.
Who had the doubt about the graph? Yes, or
It wasn't me, sir.
okay. All right, now, so this is about different type of polytropic processes. Okay. Now let's look at the last part of this chapter.
Excuse me, sir.
Yes, tell me.
Sir, can you please explain that graph once again?
अभी वही तो पूछा किस अच्छा just a second. Who is this again?
Sir?
Arvinda. Okay. Yeah, Arvinda, you only asked about the graph.
Yes, sir. I asked.
Okay. So see, what does the graph of, for example, if I have a function y equal to 1 by x, how does the graph of that one look like? Looks like a rectangular hyperbola like this. Okay. If I replace this with y is equal to some constant, like let's say 10 divided by x. Okay. So in comparison, still what it will look like? It will look like this kind of a graph only. Okay.
Yes,
But
sir.
if you compare, for example, at the value 1, this graph had a value of 1, y equal to 1 by x. At the value 10, for example, it had a value of 0.1. And at a value like 0.1, it had a value of 10. Now this second one, 10 by x, how this one varies? It varies in a similar manner, but the values are different. So at the point 0.1, it has a value of 100, so it's much above. It should be much further above, somewhere here. Okay, then at the value 1, for example, its value is becoming 10. So it's somewhere here. At the value 10, its value is becoming 1. So it's somewhere here. So this graph in comparison will be, something like this. They'll not be on paths that cross each other, but they'll just have different values and different kind of slopes. Okay. Now compare this with another graph of something like 1 by x square. Now 1 by x square will have such a thing that it passes through this point, but beyond this point, it, for example, at 0.1, it becomes 100. So it increases much more rapidly before this. And it decreases much more sharply after this. So in comparison, 1 by x square is like this. So
Got it, sir.
got it now? So 1 by x square is like, roughly speaking, let's say like this. So it's like this. Okay. So now in comparison, 1 by x cube kaisa hoga? वो और भी rapidly rise करेगा before this, and after this it will decrease more rapidly. But the point is, all these graphs are this kind of shape, whether it's like this or it's like this or it's like this. They're this kind of shape, but how rapidly the slope is changing, that depends on the power of x in the denominator, whether it is x square or x cube, and also the points also depend on what the constant in the numerator is. Okay. But the general shape of all of them is the same. So that's why what I said is important about here is not only the shape of the graph, but its comparison with an isotherm. So this dotted line that I drew, this was isotherm. So the isotherm is P is inversely proportional to 1 by V. But this one is our particular polytropic process, whereas P is inversely proportional to 1 by V cube. Okay, Arvinda, this is clear now?
Yes, sir.
Okay, so now let's move on to the last part of this applications of first law chapter, which is cyclic processes. So cyclic processes is nothing new in terms of formulae, but it's just that the process consists of individually more number of processes such that the gas is undergoing a complete loop or a complete cycle in the PV curve. Okay? So any cyclic process is actually a combination of processes such that the resultant change brings the gas back to its initial state. Okay. So it's a combination of processes, that is processes of exchange of heat and or energy, mechanical energy. Okay. Such that the gas sample undergoes a closed loop path. Okay. And returns to its initial state. that is the PV curve or any other curve like the temperature volume graph or the pressure temperature graph. But generally we use the PV graph to understand thermodynamics of a process. So the PV graph representing the process, if it's starting from this initial point here, so it has some initial pressure, some initial volume and initial temperature. It should undergo a combination of processes such that whatever the shape of the path, it should come back eventually to the final state. So the final state should be identical to the initial state, which is whatever pressure, volume, and temperature. So such a closed loop path in thermodynamics, we call it a cyclic process. In mechanics, in work energy, you'll remember we call this type of a path as a closed path. The work done in closed path is zero for conservative forces. It is non-zero for non-conservative forces. Here we call it a cyclic process. So now something that is obvious about the cyclic process is that the change in internal energy during the cycle will be zero, because internal energy is a state function. Whereas the net heat supplied during the cycle will be equal to the net work done by the gas during the cycle, and both of them will be non-zero because these are path functions. Okay. So net heat supplied to the gas during the cycle equals to the net work done by the gas. Okay, so just make a note of this definition of cyclic process. Then we'll see that there are two types of cyclic processes, as you know. One where Q and W are positive quantities, the other where Q and W are negative quantities. Okay. So let's look at a quick example.
Wait, sir.
So if we had the simplest type of cyclic process you can think of, which is a rectangular shape in the PV cycle, or the PV graph looks like a rectangular loop. Now let's say the cycle is running like this. So we have the cycle A, B, C, D, E. Okay, now let's say that this pressure is 4 atmospheres, this pressure is 2 atmospheres. This volume is 3 liters. Now given that the temperature at E is equal to, let us say, 300 Kelvin, and the temperature at C is equal to 450 Kelvin. So from this, find this volume V2 and the temperatures at B and D. And third, if the gas is a monoatomic sample, then find okay. So let us just work out this question quickly. So we can see that EB is which type of process? It is isobaric. Okay. So temperature should be proportional to volume. So temperature at B upon temperature at E should be equal to V2 divided by 3 liters. Or let's first write it like this. So it should be equal to VB divided by EA. So the unknown temperature at this divided by 300 kelvins should be equal to this unknown volume divided by 3 liters, where V2 is in liters and PV is in kelvins. Now you can see that BC is isochoric. So pressure should be proportional to temperature. So temperature at C divided by temperature at B should be equal to pressure at C divided by pressure at B. So this temperature at C is given to us as 450 divided by this unknown temperature should be equal to this ratio of volumes, which will become half. So now if we just multiply the two equations, you can see here that that will give us so V2 will come out to be how much? 6 into 3 by 2, right? So 9 liters. And once V2 comes out to be 9 liters, you can put that back over here. And from that temperature TB will come out to be 900 Kelvin. Okay, so this is a fairly easy, pretty direct, typical JEE mains type of question. Okay. Now, as far as the temperature at the point D is concerned, you did not need all this information also. You could directly see that dA is isochoric. So temperature is proportional to pressure. So temperature at the point D, you will see, will become half of temperature at the point A. That's 150 kelvins. So what is happening is that the temperature, which started from a value of 300 Kelvin here, we also given that temperature at the point C was 450 Kelvin. So first, the temperature rose to 900 Kelvin because the volume increased by a factor of 3 to 9 liters. Then your pressure became half, so temperature also became half. And then again, further, what is happening? Your volume is becoming 1/3. So temperature at the point D should be 1/3 of this. So it should be 150 Kelvin. It also agrees with the fact that from D to A, the temperature should double. So you can see all your data is consistent. Okay, so hope the first part is clear to all of you. Finding the state of the gas at each of the 4 points. Okay. Now the second part, it's actually very simple because you know that Q cycle will be equal to W cycles. We don't need to calculate both separately. We can just calculate one of them. And for calculating one of them, which will be easier? Work done will be easier because we have two processes here which are having zero work done. So I don't have to calculate work done in process DA or process BC because they are already isochoric. So I have to just calculate the work done in AB and the work done in CD and do the algebraic sum, and that will give me the net work done. And that's also very easy because it's an isobaric process. So if I have to find Q for the cycle, it's actually easier to equate it with W cycle and calculate W for the cycle. Okay, so in our figure, let's also label this volume as V1 and let's label this pressure as T1 and this pressure as P2. So for the second part, Q for the cycle or W for the cycle. So for that, we can just use the fact that since delta U for the loop is 0, so these two are equal quantities. Okay. Now W for the cycle, is easier to calculate, so we'll go with that. That is WAB plus BC plus CD plus DA. Now that too becomes further simplified because during the process DA, you can see W is 0. And during the process BC also, the net work done, the work done in those isochoric processes are 0. So these two are going to give me 0 because they are isochoric processes. And for these two, I can just calculate the work done as for this one, it is plus P1 of V2 minus V1. And for this one, it is minus, or you can just write it as P2 into V1 minus V2, which you will see is a negative form. So this one is isobaric expansion. So you'll have a positive work done. This one is, sorry, this one is an isobaric compression. So you'll have a negative work done. So this is 4 atmospheres into 9 minus 3 plus 2 atmospheres into 3 minus 9 in liter atmosphere.
Sir, it is 12.
Sorry?
Sir, it is 12. Answer is 12.
Okay. So it will be positive, no?
Yes, sir. Give me positive.
2 into 6, so it will be 12 liter atmospheres. Okay. Or you can say approximately 1200 joules. Okay. Now notice one thing also, that this Q for the cycle, which is equal to W for the cycle, which is coming out to be plus 1200 joules, it is actually positive of the area enclosed by the loop. Okay. If you see this loop, what is the area enclosed by it? This is your 6 liters. Okay. And this is 2 atmospheres. So the area is equal to 12 liter atmosphere, or approximately 1200 joules. So this is not a coincidence actually. We'll see that there's a way to prove it, that every time we have a cyclic process, Q net for the cycle is equal to W net for the cycle, which is equal to the area enclosed. But however, depending on the direction in which the cycle is going, whether it is a clockwise cycle or an anti-clockwise cycle, the algebraic sign will either be plus or minus. So finally, what the interpretation is over here, that in one cycle, 1200 joules of heat are supplied to the gas. Okay. And the work done by the gas equals to 1200 joules. So we are supplying a certain amount of heat and the gas is doing that equivalent amount of work. Okay. So that is the function of what we call a heat engine. So that is why we'll see later that this type of process where Q and W are positive for the cycle, it is called a heat engine cycle. Now we can also do it as completely unnecessary. Yeah, tell me, Beta.
Sir, how we got TD?
How we got?
Temperature at D point.
Sorry, how we got temperature at?
D point, sir.
At B point, na? Okay, we got it from the earlier equations above. So see, AB, see ये equation आया था अपने पास. So
Sir,
that was
D.
D, I'll tell you. Okay, so D is on the left hand side. I got it from DA. Okay, but you can also get it from CD. So if you compare C and D, your volume is coming down to 1/3. So temperature should also become 1/3. Or if you compare D to A, your pressure is doubling isochorically. So your temperature should also double. So temperature at D should be half of the temperature at A or 1/3 of the temperature at C. Is it clear?
Got it, sir.
Okay. Okay, now just for the sake of calculation, let's also verify this, that if I had independently done this calculation, I should have got the same. So it's completely not necessary here, but we can show this. Okay. So EB is which type of process? Isobaric. So it is NCP delta T plus isochoric, so NCV delta T or BC plus again isobaric NCP delta T or CD, and then again isochoric. So this would be a much lengthier process, but anyhow, so this will be N 5/2R because we are taking it as a monoatomic gas, okay, into temperature at B minus temperature at T plus N into 3/2R into temperature at C minus temperature at D plus N into again 5/2R plus N into 3/2R into TA minus TD. Okay. So this would have become 5/2 times P1 into V2 minus V1. Okay. This would have been 3/2 times this volume into P1 minus P2. Plus this would have again been 5/2 times P2 into V1 minus V2. And this would have again been 3/2 times like this. Each of these terms you would have got. Okay. So 5/2 into 4 into a volume increase of 6 plus 3/2 into 9 liters, but into a pressure difference of minus 2 atmospheres plus 5/2 into a volume difference, pressure into volume difference is now minus 6 liters. Then again plus 3/2 times at a volume of 3 liters, the pressure is increasing by a factor of 2 atmospheres. So this would be in liter atmosphere. Okay. If you do this calculation, even though it's lengthier, okay, you will get the same answer finally. So see, this becomes 60, okay, minus 27, okay, plus, sorry, again minus 30, okay, plus 9. 69 minus 37. So you're getting plus 12 liter atmosphere. But you can see that how much more inefficient this process is, because I'm having to apply the formula, okay, and then substitute CP, CV and all this for each of the processes. Whereas in this case, the calculation for work done was much easier. And we know by the definition of cyclic process that delta U has to be 0 because we are coming back to the initial state. So obviously the state function has 0 change. So whatever we do for the calculation, Q cycle has to finally come out equal to W cycle. Okay, so at the exam level, you have to be mindful of this so that you don't waste time calculating the Q separately, and you actually just calculate the Q cycle by equating it with W cycle, and that's equal to the area enclosed by this graph or by the cyclic graph.
Okay,
So
so
just make a note of this. Okay,
Sir.
then yes.
Sir, why was in while calculating W cycle,
Hmm.
second P2 into V1 minus V2.
सेकंड वाला नहीं है बेटा, वो थर्ड है, CD है, सेकंड वाला एक्चुअली 0 है.
हाँ सर, थर्ड वाला वही सर, वो मतलब V1 माइनस V2 क्यों था सर?
Because that is your, अरे मतलब that is the definition of work done in a this thing ना, in a isobaric process is constant pressure into change in volume. So you're going from C to D na, so your volume is changing from V2 to V1. Understand?
Okay. Yes sir.
So, and that is why in isobaric compression W comes out to be negative na, because W we are taking as work done by the gas na. So integration P dV comes out to be a negative quantity na, when the volume is decreasing.
Yes sir.
Right? Yes, that is correct, Diti. While you consider the work done from the area method, you have to consider the direction, na, whether the volume is increasing or decreasing. For expansion, it comes out with a positive sign. For compression, it comes out with a negative sign. And versus that's correct. Okay, if the direction of the loop had been ADCBA instead of ABCDA, so that is it had been anti-clockwise, then our Q net equal to W net would have come out to be a negative quantity. Okay, so just for example, in the same cycle as we were discussing just now, suppose our loop was anti-clockwise instead of being clockwise. So if we do a comparison of these two, now just assuming that the graphs are identical. So this is 2 atmospheres, this is 4 atmospheres. This is 3 liters, 9 liters. So automatically everything else will follow as the same. But let's say this one is the one we just saw. Whereas this one is in reverse cycle, or the order of the processes are in exact reverse. So it is ADCBA instead of this one, which is ABCD. So what we'll see is, as far as this is concerned, here Q net will be equal to W net will be equal to plus of 1200 joules. Okay, or basically positive of area enclosed by the loop, because it's a clockwise cycle. But as opposed to that, in this, what will happen is that Q net will be equal to W net. Now, when we calculate this in this one, it will be
Sir, both the graph are same.
won't the graph
Are same.
Sir, it is same.
ulta ho jayega na?
Yeah,
See,
ulta, हाँ, समझा, got it.
it will just be है ना. So this one here, remember what was
Sir, तो
CD over
ADC
there?
ADB है ना? ADC.
ADCBA. Okay, this is the loop.
Okay, sir, समझा.
ADCBA. So it is anti-clockwise. This is the loop ABCD. This is clockwise. Okay. So when we do this calculation here, you will see that this is equal to actually positive of that 2 into 6, so 12 liter atmosphere. But this one will become minus of 24 atmosphere. So this will become negative of 12 liter atmosphere. Okay. So this will be here exactly minus 1200 joules. So it will be negative of the area enclosed by the PV cycle or the PV loop. So this is what happens whenever the loop is anti-clockwise. Anti-clockwise PV cycle gives us negative Q and negative W, or negative of the area enclosed by the loop. So this, whatever we are seeing for this rectangular loop, we can actually generalize it for any shaped loop. Okay, so as I said that what we've discussed about this rectangular loops in particular here, we can generalize to any shape of graph. If it is a clockwise loop, then our Q net will be equal to W net, will be a positive quantity. Whereas if it happens to be an anti-clockwise loop, then Q net will be equal to W net, will be a negative quantity. So in this type of a process, what happens is that net heat supplied to the gas in one cycle is negative. Okay. That means net heat extracted from the gas is positive. Okay. And net work done by the gas, that is a negative quantity. So again, what that means is that net work done on the gas is positive. Okay. So for example, here, what this means is that 1200 joules of heat are extracted from the gas. Okay. And 1200 joules of work is done on the gas, not by the gas. Whereas here it was the other way around. 1200 joules of heat was supplied to the gas, and the work done by the gas was equal to 1200 joules.
Excuse me, sir.
Yes.
Sir, there you have written as net heat supplied to the gas in
One cycle.
one cycle. Right. Thank you.
Yes, Titi, that is correct. For any cyclic process, Q net will have to be W net because delta U is zero. No? So cyclic process means your state function's net change is going to be zero because you're coming back to your original state. So as a rule, Q net will be equal to W net for one cycle. The only thing is whether there'll be positive quantities or negative quantities, and that depends on whether the loop is clockwise or anti-clockwise. Keep in mind the loop that we're talking about is the PV loop. Okay, you should not compare this with a temperature pressure loop or a volume versus pressure loop, where volume is on the y-axis and pressure is on the x-axis. This is the standard calculation that is done on the basis of the pressure being on the vertical axis and the volume being on the horizontal axis. If some other type of graph is given to you, you have to convert this to the PV loop, and then only you can apply this formula and concept. Okay, so I think let's go ahead and discuss some of the questions from HC Verma that you have doubts in.
Sir?
Yes.
Excuse me, sir. Sir, in the second case, I mean in the anti-clockwise PV cycle, sir,
Okay.
since the Q net is in negative, it should
Yes.
be heat supplied, right?
Heat supplied to the gas is negative. Therefore, heat is extracted from the gas. You understanding? In the rectangular loop case, now the second one where I've taken anti-clockwise, Q net is minus 1200. What that means? That the net heat supplied to the gas is minus 1200. That means instead of supplying heat to the gas, I'm taking heat away from the gas. No? So I'm extracting heat from the gas. You understood now?
Okay, sir.
So negative value of Q, right from the beginning you've understood this. Na? In first law of thermodynamics, Q kya hota hai? It is heat supplied to the gas. So if Q is negative, then that means actually that much heat is being absorbed from the gas or extracted from the gas. Similarly, if W is negative, it means work is being done on the gas instead of work done by the gas. Is it clear now?
Yes, sir.
Okay. Now let's discuss some of the questions from H.C. Verma. So what we'll do is today we'll try to cover the questions of kinetic theory of gases and first law.
Sir, calorimetry.
Sorry,
Calorimetry part.
we'll do that in the next lecture.
Okay, sir.
Let's start with the kinetic theory of gases chapter because that is the background you need even before you start thermodynamics. Okay. Whereas calorimetry is not directly related; it's quite formula based, so we can keep it for the next lecture. So from the kinetic theory of gases chapter in H.C. Verma, please tell me the questions you're having difficulty with. We'll discuss. Question 22, 24, 32 and 33. Okay. So let's start with 22 and 24. Go through these questions, I'll explain. Okay, so it says hydrogen gas is contained in a closed vessel at 1 atmosphere and 300 Kelvin. Calculate the mean speed of the molecules. Okay, so what is the formula for the mean speed? How much is the pressure? 1 atmosphere. That's 100 kilopascals. Temperature of 300 Kelvin. Yeah, so can somebody tell me the formula for mean speed? Remember, it was one of the two additional formulae we had discussed. RMS is root 3 RT by M. Mean is how much? Maxwell's distribution curve. Remember, we discussed about that part. So it's 8 RT by pi M. Whereas most probable speed this was an additional formula. This is mean or average speed. And RMS, root mean square speed. So here we'll have to substitute all this. So hydrogen gas mean or average, whatever, will be 8 into 8.314 into temperature, which is 300 Kelvin. divided by 3.142 into 2 into 10 raised power minus 3. So this in kgs. Oh, sorry, this in meters per second. That will be your mean speeds formula. Now let's come to the B part. So this speed we are calculating whatever it is. Now suppose the molecules are hitting the side wall of the container, but at 45-degree angle at this speed. So perfectly elastic collisions, angle of incidence will become equal to angle of reflection kind of thing. So per molecule, how much impulse will be acting on the wall? Per collision, the impulse will be equal to 2 mb cos 45 or root 2 times mb. So now we should equate the pressure with what? The force per unit area. So pressure that will become equal to impulse per collision into, you can say like this, number of collisions per unit area per unit time. So this is what we have to calculate, I think, right? How many collisions, how many molecules strike each square meter per second? So this delta n by A into delta T, this is the number of collisions per unit area per unit time. So that is basically the number of molecules that strike the wall or impact the wall per square meter per second. That's only what we have to calculate. So this is equal to the pressure. So finally, this quantity will become pressure divided by impulse per collision. So the pressure is known to us, it's atmospheric pressure. Impulse per collision is root 2 mv. Now in this m, remember, will be molecular mass. Okay? So it is molar mass divided by Avogadro's number. So it will be 2 into 10 raised power minus 3 kg upon 6 into 10 raised power 23. And V will be this RMS speed which you are calculating. Sorry, this mean speed that you are calculating. Okay, so when you calculate this mean speed, it will come out to be approximately about 1780 meters per second. So you substitute that here and you get this factor which they're asking. And that's the 22nd question. Okay, so Tej, hope this is clear. You have a doubt in the second step, like the which one, the impulse? This impulse comes from the concept that impulse is equal to change in momentum. Okay. you can see that if the particle is coming in with a velocity like this at 45 degrees, okay, so the initial momentum is mv 1 by root 2 I cap plus 1 by root 2 j cap. Okay. Now after hitting the wall, it goes off like this, at an angle of 45 like this, but with the same speed because it's a perfectly elastic collision. So the final momentum is mv minus 1 by root 2 I cap plus 1 by root 2 j cap. So the impulse is equal to the change in momentum. So that is final momentum minus initial momentum. So when you implement this, you will get j as 2 times mv 1 by root 2 I cap. So the magnitude of the impulse will come out to be like this. Okay, for the pressure is force per unit area. Now see, what is force? It is impulse per unit time, rate of impulse. So impulse per unit time will be equal to impulse per collision into number of collisions per second. Okay. So pressure, which is force per unit area, is 1 upon area into impulse per unit time. And the question, they have actually asked you to solve for this thing only. They have asked you to calculate this quantity only. So that quantity is how much? It is pressure divided by impulse. So that's how we are getting this formula for it. So hope this is clear now. Okay. Force is rate of change of momentum, and change in momentum is impulse. So it's rate of change of impulse like that. Okay, let's come to question 24 next. Oh, you want to write down? Okay. Okay, just try to take this down quickly. And those who have finished writing down, go through question 24. Okay. I'll give you a hint quickly. In question 24, the hint is you have to just use ideal gas equation, PV equal to nRT. By the time the gas after leaking out reaches the final steady state, the pressure and temperature inside the container should be the same as the atmospheric pressure and temperature. The initial pressure and temperature is known to you.
Sir, in question 21, should we take average speed or mean square speed?
Okay, so hope you must have figured out 24th question by now. Okay, Kshitij, I'll discuss 21 also after discussing 24. So in 24th, what is happening? You have a closed metallic jar. Which initially has oxygen at a volume of 1 liter, pressure of 1.5 atmospheres, and a temperature of 300 Kelvin. Sorry, temperature of 400 Kelvin. Whereas the surrounding atmospheric pressure is this much, and the surrounding temperature is 300 Kelvin. So what is happening is right now the number of moles of oxygen that we have is N, and PV is equal to nRT. Now after the leakage, the pressure becomes equal to atmospheric pressure. The volume of course remains the same. The temperature becomes equal to surrounding temperature. So now we have P prime V is equal to N prime times R into T prime, where N prime is equal to N minus delta N, where delta N is the number of moles leaked out. Okay. This will become P naught V is equal to N minus delta N times RT. So comparing these two equations, we can see that sorry, into 4 by 3. My mistake. So half the oxygen gas leaks out. So mass of oxygen that leaks out, we can find out. So delta N is actually equal to N by 2. So this is the mass of gas that leaks out. These many grams of oxygen leak out. now see N is equal to PV upon RT. So what is delta N? The number of half of N leaks out, no? Okay. Okay, so next let's come to question 28. So question 28 you can now do very easily by using polytropic equation. But because this is in kinetic theory chapter, let me do the question by just using the kinetic theory of gases concepts only. Okay. So during an experiment, an ideal gas obeys the additional law that PV square is constant. Okay. So for me now this becomes very simple using polytropic equations, but I will not do that. I'll use basic kinetic theory of gases only and solve. So the gas is initially at a temperature T. So initial temperature is T, initial volume is V. Now the final volume is becoming 2V. Okay, this is very simple. Okay, so we have to find the final temperature. So PV square is constant. That means now P is proportional to T by V because PV is equal to nRT. So that means T by V into V square is constant. That means temperature into volume is constant, or temperature is inversely proportional to volume. So final temperature upon initial temperature is initial volume upon final volume. So final temperature will be T multiplied with V by 2V. So it should become half. So you'll see that if you revisit these doubts you had earlier, might be that right now you'll find them quite easy to solve because nothing much in it once you have done so much of thermodynamics. At that stage you were just learning the concepts initially, so it might have been tough. Anyhow, let's move to question 31. 31 is one of the more slightly technical questions. So the hint I'll give you in 31 is that conserve total number of moles in the container A plus B, and also conserve total internal energy because it is heat sealed. Okay, that is the total kinetic energy of gas molecules for A plus B. So applying these conservation principles, okay, you'll be able to find out the final answer. Just try this out. Oh, last sum you want to write down. Okay, okay. Okay, Tej, I'll take you back to the last question. Okay. In the meantime, you can also write down question 28 solution, which is actually very easy, but okay. Okay, so those who have finished writing down the earlier question, please move on to question 31. Okay. Solve it by the two hints I've given you: conservation of total number of moles and conservation of total internal energy.
So done.
Okay, so hope this question is done now. 31st question. So at these two vessels, okay, which are connected by a tube which is initially closed by a valve, okay, and assume that initially the gases were maintained at different temperatures by some kind of mechanism. Okay, so we had with the valve closed, both having the same volume, I think. Yeah. So PA, V and TA, PB, V and TB initially. Okay. Now after opening the valve, okay, the gases mix. Okay. So they reach a common equilibrium pressure and temperature T. Okay, so we have to show that P by T is equal to this much. So one way is that PA into V is equal to NA into R into TA. PB into V is equal to NB into R into TB. This is initially. And finally, P into 2V should be equal to N into R into T, when the final state N should be equal to NA plus NB. I think just solving this equation alone, we don't have to really worry about the energy here. And also we can't, because we don't know whether they are both monoatomic or diatomic, etc. So with the absence of information about the type of gas, we can't do the conservation of internal energy. We just do conservation of total number of moles. So N is equal to Na plus Nb. So 2 PV upon RT, that is N, is equal to PA upon RTA plus PB upon RT. So you can see that P by T is equal to 1 by 2 . So actually the way of solving the full problem now, because see, there are two unknowns, pressure and temperature. So conservation of moles will just give you this. But additionally, if I had information about this now, then I could have said that, okay, internal energy in the first is okay. This is initially. And finally, so I would have got this kind of relation that
Then
so this would have given me a second equation, and solving the two equations, we could individually solve for P and T. Okay, so this would have given the temperature, and then we would have substituted this in this first equation. That would have given the pressure. But in this question, you were just asked to solve to prove this first equation and nothing else. So you didn't have to do the analysis about the energy. Okay, so here, of course, FA is the degrees of freedom for gas A, and FB degrees of freedom for the gas in sample B. Okay, people. So with that, we'll conclude today's session. Tomorrow we'll, I think tomorrow itself, right? We have another lecture. So we'll finish. We'll try to complete all the doubts of kinetic theory of gases, first law of thermodynamics, and molar specific heat capacities. That is these chapters in today, tomorrow. Okay. Then if anything is pending in calorimetry or your DPTs from earlier, etc., we can pick them up in later lectures. Okay. Before we start with the next section, which will be heat transfer. So heat transfer will be a new section which will be kind of unrelated. Yeah, we'll try to cover all the doubts tomorrow. Okay. But first priority, let's finish the thermodynamics doubts. Okay. Then only we'll pick up the other chapters. Okay. So in case the doubts are from some few days back and all, just try out those questions again, because with the number of questions you've done in class now, you should be able to solve quite a few of them yourself. Okay. In retrospect. Okay. So that way we'll have more time to solve doubts from other chapters also. Anyhow, that's it for today, people. Wish you all the best.
Bye, sir. Thank you so
Bye,
much.
sir. Thank you.
Okay. Bye, people.